Where? Oh, and it's available one. You can wear. Yeah, but I'm not sure which one. So which of these is the correct one?
Those are. Both are. I mean, both are waiting for the. And only that was going to be able to do modular. So you will have to take one of these and
One of these.
both of these. Well,
Careful.
yeah, so during Q&A, maybe I guess I'll be playing surround.
With this one, do I have to keep it close apart?
Yeah, I think maybe on two sides of your sleeve. Yeah, I think that should work.
Can I use both? Can I use it? Very wonderful.
Oh, yeah, that was good.
But this has nothing in it.
It's just, it's not.
Oh, this is.
I guess you will have. Hello, hello, testing, testing.
No.
Yeah, it's yeah, the audio is working now. Yeah, depends on how you do it. I just off down. Well, you can use the room for the microphone. Yeah, okay. Yeah.
So if they start at 10 after the hour.
10 after the hour, yeah.
Yeah, because all the classes end on the hour. They take up time for students to move forward.
Yeah,
Yes, then start at.
okay, good, yeah. Then I before, set 5 minutes before 4, you can.
I can
Send
add
me.
here, so
Yeah.
I can.
Yeah, yeah.
And let me know, so if you're doing, or you can let the audience. terms of questions. If you prefer to have it after the talk, that's fine. You bring the talk, you can let them. You can keep them from there.
I think they can ask us. Yeah,
You can just let
yeah. If there is- Yes.
Yeah, but I guess you should, no, I guess you should still use it because then people on the Zoom can hear it. Because this is how you talk to Zoom, right? Oh.
Nine.
All right. Good afternoon, everyone. This mic is not working, but so I'm just going to yell. It's my great pleasure and honor to introduce Professor Damson from the University of Chicago. So Professor Son got his PhD from the Institute for Nuclear Research in Moscow. After spending some years at as a postdoc at the University of Washington and MIT, he's been on the faculty at various places, including Columbia, and then many years at the University of Washington, and for some years now at the University of Chicago. And his work spans a huge number of different areas where he's had a lot of impact, thinking about quantum chromodynamics, thinking about nuclear physics, thinking about the physics of black holes, and what's called the ADS-CFT correspondence, to thinking about the correspondence with field theory. And he's also worked a lot on the quantum Hall effect, where he's had a lot of influential work in the area. His work has been, widely recognized, and he was a recipient of the Bogolubov Prize and the ICTP Dirac Medal some years ago. And today he's going to tell us about the connection between, in some sense, two of the fields where he's worked on, but bringing them together, thinking about this connection between gravity and quantum Hall effect and how there is some relation between them. So please join me in welcoming Professor.
Thank you very much, Arun. It's my great pleasure to give this colloquium. I'm going to tell you about the emergence of particles that in some sense is similar to the graviton in the quantum Hall effect. So here's the plan of my talk is first to tell you about the graviton, and then about the fractional quantum Hall effect. And then I'm going to explain the notion of a quasi-particle that usually called the magnetoroton in the quantum Hall effect, and discuss the value of its spin. And then I'm going to briefly discuss the recent experiment, which claims to observe a condensed matter analog of graviton in a solid. So somehow I cannot. Okay, so the origin of the word graviton. As a term in physics, graviton was a term that appeared in printing somewhere in 1934. In the first time, it appeared in a paper with the title, The Hypothesis of Neutrino and the Law of Energy Conservation, written in Russian by two Soviet physicists, Dmitry Blokhintsev and Galperin. And here is the reference. The journal you see is not a known one. It's under the banner of Marxism. Blokhintsev is the more, I think, more senior author of this paper. He later became a first director of the Joint Institute for Nuclear Research in Dubna, and he played some role in the setting up of a research lab in nuclear energy. So Blokhintsev, at least in his later career, was a more practical physicist. But this paper is a very theoretical paper. The interaction. Okay. Okay, here's a copy of one of the page. I think one of almost the last page. When he suddenly, after the discussion of the neutrino in the previous large part of the paper, he wrote, "It is quite interesting to compare the properties of the neutrino and those of the so-called gravitons." And the observation here is that both particles interact very weakly with matter, so maybe they are related. And then they wrote, if neutrinos are in fact gravitons, then this would mean contemporary physics has managed to eliminate the existing border between gravitation and electromagnetism. However, it is difficult from theoretical consideration to identify gravitons with neutrinos. You can see here, actually in 1934, there are a lot of things that we now perceive as obvious that wasn't obvious for the authors of this paper. For example, it's clear now that neutrino cannot be graviton because one particle is fermion, the other is boson. But at that time, this seems to be not very clear. A more concrete attempt to quantize gravity was made 1 year later by Matvei Bronstein. It is also possible, I read, that Bronstein is the person who used the word graviton when discussing physics with these authors. That's why they wrote the so-called gravitons. Someone must call that particle gravitons before. So that might be Bronstein. Bronstein is another Soviet physicist who wrote a paper in it's published in 1936. He wrote it in 1935, quantizing the linearized theory of general relativity. In particular, he found, for example, that there are gravitons, the particle that is obtained after the quantization, has two polarization, as I will illustrate later. There's two polarization that can be thought of as the component H12 and H11 minus H22 if the graviton propagate in the third direction. So here is the explanation. First, let me explain the polarization of photons and then talk about gravitons. We know that photons also has two polarizations, and at the level of classical electrodynamics, these correspond to two circular polarization of the electromagnetic waves. If we sit at one point and look how the electric field changes with time, then we can distinguish the left-handed or right-handed polarization of the photon. And one corresponds to photons with spin pointing along the direction of momentum, and the other polarization is photons that have its spin pointing in the direction opposite to the direction of motion. So the components of spin on the direction of motion of the photon is either +1 or -1. Photon is usually said to be a spin-1 particle, but the projection of the spin of the photon on the direction of motion can be only +1 or -1, can never be 0. That's the properties of a relativistic particle with 0 mass. Now, a graviton is similar. There is a similar situation here. We can imagine looking at a gravitational source and try to detect the polarization of the graviton coming to us in the following way. So let me arrange test particle in a circle and then see how the distance between these particles changes if a gravitational wave moving through this circle. So you can imagine that gravitational wave moving toward the screen. And then two circular polarization of the graviton correspond to the case when this ellipse rotates in the clockwise or counterclockwise direction. These two cases correspond to graviton with spin parallel or anti-parallel to the momentum. So in these two cases, the projection of spin on the direction of motion is +2 or -2. So spin 2 particle is the graviton, but its projection, the projection of spin on the direction of motion cannot be cannot receive any intermediate values, +1, 0, or -1. It can be only +2 or -2. That is what Bronstein found when he quantized Einstein theory of gravity. If there is any question during my talk, please interrupt me at any time. Unfortunately, Bronstein perished very early, soon after writing his famous paper. Deser and Starobinsky wrote in the introduction to the English translation of the paper that had Bronstein's life not come to a tragic end. In Stalin purchase, he would certainly have fulfilled his promise as the most valuable contributor to theoretical physics.